Okay, so in this video we're looking at section 7.5, the piecewise function. Okay, so to start off, we need to go back and revisit the domain of a function. So what is the domain of a function? Well, it's the set of all input values for which the function is defined. Okay. All the functions that we've looked at in this year have had a domain of all the real numbers. In other words, we can substitute any value we want for x into the equation. We haven't really looked at any functions that restrict or anything like that. Well, we need to talk about that. We need to talk about a restricted domain. What is that? A restricted domain is when I place a limit on the values of x that we can substitute. Okay, so there's going to be a requirement that it has to be, usually it's in the form of an inequality, some numbers bigger than or less than that. So it's usually in the form of an inequality. So here's an example I'm going to show you. So here's a graph. This is the graph of a line, mx plus b. So the slope would be 2, the y-intercept would be 1. But I want to graph this on what's called the restricted domain of x greater than negative 2. So this restriction right here means that I can only plug in numbers that are greater than negative 2 for this to be defined. There is no numbers below negative 2. You cannot plug in negative 3 into here. It doesn't exist. So you're not going to get the full line that has an arrow on both ends. You're going to get a piece of that line. Kind of like, well, you haven't had that word yet, so let's just take a look at it. So, but how do I do this? Well, like normal, you're going to graph, make a table. It's one of the reasons why I have you make a table. Okay, since it's a line, we're going to make a table with 3 points in it. But because of the restriction, okay, think of the number line, x is greater than negative 2. You're going to put in this number, negative 2, into here, and that becomes what's called the boundary point. And then you're going to plug in numbers greater than negative 2, following the number line. So you always want the boundary number in there, and that's this number right here. Okay, it may or may not be included. We'll talk about that in just a moment. And then I want numbers greater than that. Okay, so that I have a total of 3 in here. So if I take these negative 2, negative 1, 0, plug them in, I get these values right here. Okay. Now, this is an inequality, this restriction, and it's strictly greater than, which means negative 2 is not included in this domain. So why did I graph it? Well, I graphed it because I have to know the boundary. And sometimes the boundary is included and sometimes it is not. This is an example where it is not. So if you look back, and we talked about this before, the boundary, if it's one of these symbols, is going to get a circle, open circle, which means not included. And then if it was included with these symbols, then you would put a dot. Okay? So when I graph this, I'm only going to put the graph when x is greater than, based off of the restricted domain. So notice that only the graph from negative 2 on the x-axis and greater is being graphed. This bottom part is not being graphed. This is the boundary point. It gets a circle because of that symbol. And then all the other dots, and then I just draw the arrow in one direction only. Always label the boundary point and one other point on your line. And this is what a restricted graph looks like. Okay, this is what we're looking for, a piece of the whole line. And I want only the piece that is when x is greater than negative 2. With the open circle here, there is no value to this graph there, but it is the boundary. So the moment you come off of negative 2, then the dots start being included. This is a restricted domain graph. Okay? You want to be very careful here. You want to draw the portion of the curve or line that's described by the restricted domain. Don't draw the wrong one. Make sure you label your endpoint or endpoints if there's more than one. And any other points you need to draw the graph. Once I have this concept of what a restricted domain graph looks like, then I can talk about this thing called a piecewise function. A piecewise function is a function that is created from pieces of other functions with restricted domains. So would be a piece of that graph. And so if I have another piece graphed at the same time, then this becomes what's called a piecewise function. Okay? And I'll show you how that works. We're going to talk about a famous one, piecewise function that's used in many different situations that you are familiar with. The most famous piecewise function is, in my opinion, the absolute value curve. F of x equals the absolute value of x. Because the absolute value of x equals x when x is greater than or equal to 0, and it is equal to negative x when x is less than 0. Okay, remember, absolute value means always positive. So if I plug in a negative 5, if x is negative 5, I need the opposite of negative 5 to make it positive 5. That's what this means, the opposite of. And so I can think of an absolute value graph as a piecewise function. It is x when x is greater than or equal to 0, and negative x when x is less than 0. These two things are called the pieces. These are called the restrictions. And this number is called the boundary point, or also called the separation point. Okay? So 0 is a boundary for each piece. It is where the two pieces separate, where one starts and the other one stops. That's what this means. It's a boundary point, or you can call it a separation point. All right? So let's take a look about how we would go about graphing one of these things. So I have an example we're going to do. Okay? And just like all things, how do I graph this? It's just to restrict. Each piece is a restricted graph. So you graph each one individually with their restriction. So for the top piece, what I usually do is this. I'll make a table for that piece because it's a line. And I usually do the table this way. I'll put X here, and then I'll write the name of the piece here so I don't forget which table's for what. Okay? This is the separating point or the boundary point. I want all the x's less than 1. So if I look at a number line, 1's here, and I want all the numbers less than that. So 1 is the end on this side. So I usually put it on the end here. And then I pick numbers smaller than 1. I do that so that my table matches what my graph is going to do. Okay? I also do this. Because that symbol is a less than or equal to, I know it's going to have a dot on that end. So I usually put a dot right there, telling myself that this is going to be a dot when I graph it. So very quickly plugging these numbers in here, you'll see that I'll get -1, -2, -3. And we can draw that piece right now if you wanted to. So let's go ahead and do so. Put a dot at 1, -1. And it is a dot. It is an endpoint. 0, -2, and then -1, -3. And you can see the pattern that's emerging. And so we just continue that out. So it's a piece starting here and going down this way. So starting here, line everything up, and draw that piece. And put an arrow on the end. Arrow only on one end. This boundary point right here is going to get a name, and then some other point will get a name, but I do the names last. So that piece is done. Let's go graph the bottom piece. So I make a table also. And then this one is -2x plus 3. And I want all the x's greater than 1, from 1 and greater. So that means 1 is going to be on the left, and then the other numbers are bigger. So I'm going to start that one right here. And because of the symbol, I know it's going to be an open circle. And 2 numbers bigger than 1 would be 2 and then 3. Taking those numbers and plugging it in, I'll get 1, -1, -3. And let's go graph those. Okay? So 1, 1, 1, 1 gets a circle. Then 2, -1 gets a dot. 3, -3 gets a dot. Every other point gets a dot except for that first one, just a circle. And so then I connect those into a line. Arrow on the end. Okay. I have to label things now. This point, even though it's not included, still gets the name. All boundary points get named. And this one gets named 1, -1. And then one more point on each branch, whichever one you choose. So I can do this point here is 3, -3. And I can do this one over here, -1, -3. I can also have done the 0, -2. Either one's fine. So this one I know is a glare that looks like it. This is a dot. That is a circle. Now, a couple things that people have a tendency to do wrong here, and you should never get this wrong, is this. This is a function. So remember, it has to pass the vertical line test, which literally means there are no overlaps. The pieces do not overlap each other. You may think, well, these overlap right here. No, they don't. This one is included, and that piece is not. So there's only one dot here. Okay, they cannot overlap. And so that's important to understand because you're going to be asked to evaluate functions and stuff like that as we go through this, a piecewise function, and you need to know how to plug in your numbers appropriately. So remember, if you're graphing and your graphs overlap, you've done something wrong. Okay? And just make sure that everything works out. If all the x's are less than 1, then pick a number less than 1, and what should I get? Look at your graph and make sure you graphed it properly. Another area that people do wrong is they'll graph the wrong piece. Instead of this piece, they'll graph the opposite side piece, and that's not true either. So that's how I would graph a piecewise function. Here's my notes. I'm going to lay it up here so you guys can see what I did and how I wrote it out. So this is the example we just did. But this way you can pause if you wanted to write down those notes over there. Okay? Now, the next thing you got to be able to do is we need to be able to write a piecewise function from its graph. So let me show you what I'm referring to. Here is a piecewise function. I want to write the function for this, the equation for this. And so how do I go about doing that? Well, here's how I do it. Here's what I'm going to do. First thing first, I'm going to look at my picture. I'm going to identify the boundary points. Okay? The boundary points will either be a break in the graph like this, so you can see clearly what x value is the boundary, in this case 1. Over here, or it's going to be where they have a corner. See, we have a corner right here. That's the separating point or the boundary point. Again, in this particular example, is that x equals 1. So that's important to know also. We're going to write the equation of each piece according to the rules of that type of function. So if I have a line, it's how do I write the equation of a line? If I have a quadratic, it's how do I write the equation of a quadratic, absolute values and things like that. What's important to remember is this, your equation, no matter which one you have, or however you solve it, get the equation for it, you have to make sure that you write it into y equals form. Okay, you cannot have it all over the place. So if it's a line, it has to be in slope-intercept form, so y equals mx plus b format. You'll have to make sure it gets into that form. Same thing for quadratics and stuff. You need to have a y equals. And just like anything else, follow the template. The symbol is determined by the endpoint. If it's included, then it gets a dot, and if it's not included, it's a circle, and then you're going to have these symbols associated with that. There is a special note. If the endpoints coincide, that means they overlap. So one is a circle and one is a dot, as in this case right here. See, you can't see which one's the circle or which one's the dot because they are on top of each other. So what happens is you're going to do a simple thing like this. The top piece will get the less than or equal to, and the bottom piece gets the greater than. That's how you're going to take care of that. Okay? So here's my template I'm going to follow. The left piece equation will go here. You're going to put in one of these two symbols, depending on what the endpoint is. And then this is the separating point or boundary point. The right piece equation will go here. And you don't need the y equals part. You need it in that form because this is the y equals. So y equals that, y equals that. See, look at this. There's no y equals in here also. This is the y equals that, y equals that. That's how that works. And then this symbol down here is either this symbol or that symbol, and then the boundary point there also. So this is what we're going to follow. Let's go do that on this next page over here and show you how it's done. So we've already determined the separating point. We talked about it. The boundary point is right there. So our boundary point is 1. Okay? Both of these pieces are lines, so we need to find the equation of a line. To write the equation of a line, we need to have the formula y minus y1 equals m times x minus x1. We need a point and a slope for each piece. Okay? We're going to do the left piece first. The left piece first. Organize yourself so you don't get confused with what you're doing. Here's the left piece. And just like we do any kind of equation, what I usually do is I just put a little quick XY table here. I have the point -3, 2, and the point 1, 4. We're looking for the slope. So my slope is, remember, the change in the y's over the change in the x's. Here's the y change is a +2. The x change, be careful here, is +4. Okay. And so then I get 2/4 or 1/2. So that's the slope of this line is 1/2. And it should be positive because it's going upwards. So it should be a positive slope. Okay. So I need a point slope. There's my slope. I need to pick a point. Let's pick this point right here. Okay. It doesn't matter which point I pick. I can pick the 1, 4 if you want. It doesn't matter. Let's just go ahead and use that point right there. So we'll have y minus 4 is 1/2 times x minus 1. And remember, we have to get it into y equals form, so we're going to have to distribute this and then move the 4. So in doing so, what's going to happen here, and you can check my math, it's going to give me a 1/2 x, and then I'm going to have plus 7/2. So that is the left piece right there. We're going to do the exact same process for the right piece. We're going to have a little XY table here. We have the numbers 1, 4, and then the number 4, -2. We got to find our slope, the change in the y over the change in the x. So this time I'm going down 6, and this one is going up 3. So I've got a -6/3, which is a -2, which makes sense because this line is indeed going down in a negative fashion. It should be a negative slope. I can use the same point if you want. Y minus 4, -2 times x minus 1. And I can only use the same point. It's on both curves. Okay. Solving this out, just like before, solving for y equals, and I get the equation -2x plus 6. So there's the first piece, the left piece. This is the right piece. And our separating point is 1. So using our template, here's my equation. So f of x equals a little curly bracket like so. The left piece goes in here, not with the y equals, just the other side. So this is going to be a 1/2 x plus 7/2, comma. And it's going to be what? X. Okay, it's the left piece, so we're going to the left, so it's going to be less than. And remember what I said, if you can't tell which one it is, the top piece gets the or equals to. Since I can't tell which one is which, the top piece will get the or equals to 1. And then the bottom piece, not the y equals part, just the other part, -2x plus 6, comma, and then x is greater than 1. And that is how you write that function. Okay? And so the last part I'm just going to show you so you can understand here is how do I evaluate? Okay, how do I evaluate? And that's important to know because a lot of people do this wrong also because they forget that this right here is a function. How do I evaluate a piecewise function? For any number k that you pick, to find f of k, you're going to substitute that number in for the variable for only the piece where it is defined. Never substitute a value into both pieces, ever. Only into one of the pieces. So in this example here, I'm showing you, find the f at 0, that means to plug in 0. 0 is only defined in the top piece. This is for all numbers less than 1, and 0 is less than 1. This one is when numbers are bigger than 1. So it's not this piece at all. So you only plug it into the top piece for x, and when you get done, you get 7/2, and so that is the value of f of 0. And this is how you would display it, by the way. Okay? F of 3 is a number bigger than the separator. So 3 is bigger than 1, so we're going to plug it only into this piece right here. So if I plug in 3 into this piece right here, I get -6 plus 6, which is 0. And so that is my solution. F of 3 is 0. Now, if you don't think too hard on this, let's go look at our graph. F of 0 was 7/2, so that's like 3.5. At 0, what's my graph? Oh, it's 3.5. So you have to right between 3 and 4. And over here, when I plug in 3, I'm supposed to get a 0. Well, guess what happens at 3 over here? The graph goes through 0, doesn't it? See, so you can see from the graph what your solution should be. But if I don't have the graph drawn, remember, you only draw it into the piece that it's defined for. So that is piecewise functions. You're going to be asked to graph them and to evaluate them and to write the equation from looking at one. Okay? And so we'll do all that together in class.